Okay, welcome back. I'm not exactly sure what I want to do. I do want to read more of the Python for DevOps book, but now that I'm freed up on the Wired networking series, I think kind of the most exciting thing I want to do is a Cisco design guide here. So that is what I am going to do. So let's go to and that will help me for my Cosmic Python series I'm doing, because I wanted to walk away from that with a really well-designed network automation, ZTP device stand-up project using Python. So I'm going to need to know what to configure all of these devices with in this topology, and I set up this topology in accordance to this documentation here. So this is still the Wired networking series. We're focusing on network engineering as you would just find it available free out in the wild and not in a classroom or on a test. So these free public design guides offered by Cisco definitely fall into that category. Alright, so we'll start with the definition and introduction. And I actually want to take a quick break on which I haven't even started the video yet, but I'll be back shortly. Alright, sorry about that, but that was completely necessary. Alright, so this is introduction, actually it's definition and introduction, campus WAN and campus LAN and wireless LAN. There is a tendency to discount the network as simple plumbing, to believe that the only design considerations are the size and the length of the pipes or the speeds and feeds of the links, and to dismiss the rest as unimportant. Just as the plumbing in a large stadium or a high-rise building is designed for scale, purpose, redundancy, protection from tampering or denial of operation, and the capacity to handle peak loads, the network requires similar consideration. As users depend on the network to assess the most important, is that access or assess? I'm pretty sure it's access. Yeah. Access the most important information that they need to do their job, so I think they're going to talk about security here, and to transport their voice or video with reliability. The network must be able to provide resilient, intelligent transport. The reliable network design also needs to incorporate versatility in order to address the changing needs of an organization. Okay, they're not going to talk about security. Here are some key concepts that you should address when creating a reliable and versatile network design. The network should be always on and resilient, continuously on and available, and resilient. So if something goes wrong, your network can still function until you get it fixed. It's not a hard stop once there's a problem on your network. Intelligent, adapting to changing needs beyond the beyond the limits of basic standards, using insight into network activity. So if you need to scale out your network, you should be able to do it intelligently and just say, oh, I need a switch here, instead of saying, oh, I need an all-duet network because this one link is saturated with traffic. Secure, protecting the organization and its users. So this one is definitely more self-explanatory. I mean, to be honest, like I think a lot of network attacks, if you can reach the network, it doesn't, like I doubt a lot of attacks happen that way. I think the most common way a organization and its users are breached is through email attacks. Like the users just give the bad information, and, like, so I'm just not sure there's a lot of red team or bad actors exploiting network vulnerabilities. But I could be wrong. I really am not at this point learning about security as kind of my main thing. So I definitely don't have a complete sense of what kind of security threats are out there. Let's look that up though, actually, because that's interesting. Kind of cyber security threats are out there. So here are the 10 most common. Malware. Yep, that's what I thought. Phishing, spear phishing. That's what I thought. So here's where you could have a network attack, a man-in-the-middle attack. That's basically an attack on your network. Trojans, ransomware, denial of service. Here's another one that can be a network attack. Attacks on IoT devices, data breaches, malware on mobile apps. So yeah, it looks like there are some common attacks, denial of service and man in the middle, that a insecure network really could cause that as a problem. But I think even in these, I don't know, that's something I'm actually interested in getting a bit more into at another time. Planning for the future. As you look at a network design, consider the following networking trends and future needs of an organization. So this word future, okay. This was updated May 4th, 2020. I want to make sure I wasn't reading a guide from 1995 like I was with the BGP RFC. I mean, a lot of that is just the standard, so it's not going to change. But for a design guide, I definitely want that to be up to date. The network must be ready to appropriately scale over time in order to meet the demands of the organization it is supporting. Because demands on wireless access points, APs, with the latest standards, including Wi-Fi 6, 802.11ax, technology exceed 1 gigabyte per second, and the IEEE has ratified the 802.3bz standard that defines 2.5 gigabyte per second and 5 gigabyte per second Ethernet. You should deploy a network that is ready to support the demand without requiring an upgrade of the existing copper wiring plant. You accommodate these latest demands by deploying network platforms, including Cisco Catalyst multi-gigabit technology. See, this Cisco guide is going to be a little bit frustrating because it's going to be like, oh, how do I scale up my network? How do I make sure my network can scale? Well, use the Cisco scaling compatibility tool. It's like, no, I'm not going to do that. I just want to understand the concepts behind this. But let's look into this. So here's multi-gigabit technology. So let's look at the products, and let's just take a look at what features these have in common. So yeah, so we've got 10 gig ports. All of these appear to have 10 gig ports. I guess I'm not sure what this has. Oh, this has gigabit. So I'm surprised this one's still out there. It doesn't seem to have enough bandwidth, but this looks good because it's got 10. It's got 1, 10, 25, and 40. So if you buy this, you're going to be good in long term. This long term because you got that extra 100. But this I think is probably the best investment long term because you've got that. This one looks good too because yeah, I mean, it just depends on what you need. But let's look into this one. Yeah, and you can't get the prices on these. It's one of those things where like if you have to ask how much it is, you can't afford it. But like that's frustrating because like people are like it costs a certain amount of money. Like I'm not the person paying for it. If I'm gonna buy something like this, it's gonna be like I need to know the price in order to meet the requirements of the budget and not go over the budget. So it's kind of frustrating that they don't show the price. Luxembourg? What the heck is going on with Luxembourg? Alright, something's happening in Luxembourg, but let's skip that and move on. I do deploy new devices with higher power requirements such as lighting, surveillance cameras, virtual desktop terminals, remote access switches, and APs. Your design should have the ability to support power over Ethernet up to 90 watts per port, offered with Cisco Universal Power over Ethernet Plus, and the access layer should also provide power over Ethernet perpetual power during switch upgrade and reboot events. The Cisco Catalyst 9000 series access layer switches are perpetual PoE capable and ready for 100 watt per port as that technology becomes available. So I guess there's something to be said for buying more than what you need. Or you could just get this for less. But here you just get you don't get you just get a gigabit. But at some point I will be building out like a home network. Right now I'm just in an apartment, so that will be interesting. Compliance issues drive a choice of platforms required when you support standards, certifications, and MACsec. For those cases, you should also be prepared to make analytic data available using technologies such as NetFlow. The Internet of Things, IoT, impacts today's network design. Your network should support TrustSec and other segmentation and virtualization technologies, such as Cisco Software Defined Access, SD Access, in order to enable the scale and expanded uses and policies for the network driven by these trends. Bandwidth needs are doubling exponentially multiple times over the lifetime of a network, so that the network deployed today needs to be prepared to aggregate using 100 gigabit per second Ethernet and 25 gigabit per second to 40 gigabit per second to 100 gigabit per second capacities or more over time. The network platforms deployed today should offer the best longevity into the future versus selecting the equipment that only meets the limits of today's need. See, I don't know if I agree with that though. Like, there's got to be a trade-off, because if you buy a future-proof device, yeah, you don't have to swap it. Yeah, it can seamlessly work going forward, but at the same time, how much more is that going to cost? And is there a point at which you can buy a device that meets the limits of today's needs for $1 instead of buying a device that you'll never have to replace for $1 million? And then, if you eventually have to replace the one that meets today's needs because you have new needs, that means spending another $1 on a new device, and yeah, you've got the extra work you got to do. You wouldn't have to have done before, but obviously in that sort of scenario, which is clearly not a real-world scenario, you are better off purchasing a device that meets the limits of today's needs because you just save so much money. So, and that's another reason why it's so frustrating that the prices just aren't transparently listed. So this is the one I'm most skeptical of when it comes to planning for the future. The rest of these are pretty clear on no argument there. But this, especially since this says that bandwidth needs are doubling potentially multiple times over the lifetime of a network. So if you have a network and you think all you need is 10 gigabit per second, that's going to double to 20 to 40 to 80, which I guess you're fine with here, but yeah. So this I'm not too skeptical of. I guess I'm a little bit skeptical of that because I just want to see how they determined this and how long the lifetime of a network is and what they consider an actual network, because like a lot of networks are you're swapping out routers and switches when you need to double the bandwidth needs and all that. So like, is that one network or is it? So I'd like to see a little bit more of that, but I guess I'm not really skeptical of this claim that bandwidth needs are doubling potentially multiple times over the lifetime of a network. It just seems intuitive to me that is true with Moore's law and all that sort of thing. And most vendor, like I remember myself, 1 gigabit per second was high speed, and now we're having devices with 100 gigabit per second. So this is intuitive. I'd like to see more about it, but I have no reason to doubt it really. This one I do have a lot of reason to doubt. I just need to see the numbers, and especially if you just have a maintenance window, have auto deployment, auto configuration, everything really nice as far as network management goes. I could see this one. I'm skeptical that it is better to buy equipment now that costs more, but that you're less likely to have to replace later. To reduce operational complexity, you can use a centralized controller with open APIs, allowing for a very fast, low-risk deployment of network devices and services through UI, user interface, and existing orchestration systems. Cisco Digital Network Architecture Center, Cisco DNA Center, automates this network device configuration and management to achieve your organization's intent. I'm gonna copy this, do a find, and I just want to see. Perfect. Okay, good. Because I saw this big bar here. I'm like, oh God, is this just for one section or is it for the whole document? And it's for the whole document. So by the time this slider bar is at the end, I'll have finished this. Perfect. Cisco Digital Network Architecture, Cisco DNA. Cisco Digital Network Architecture, Cisco DNA, provides a roadmap to digitization and a path to realize immediate benefits of network automation, assurance, and security. The Campus Local Area Network, LAN, is the network that supports devices people use within a location to connect to information. The use of the word campus does not imply any specific geographic size or organizational boundary. The campus LAN can range in size from a single switch at a remote site up to a large multi-building infrastructure supporting classrooms, carpeted office space, and similar places where people use their devices for their daily activities. The campus design incorporates both wired LAN and wireless LAN connectivity for a complete network access solution. This guide explains the design of the campus wired LAN foundation, how the wired LAN, is that what that stands for? I don't see where that's defined. Extends secure network access and is exclusive network access for your mobile workforce. Oh, I think WLAN stands for wireless VLAN. I thought it stands for wired LAN because it said wired LAN right there. No, it's not defined. I think this stands for wireless. How the wireless local area network can provide guest access for contractors and visitors to your facilities. If you didn't download this guide from Cisco Community or Design Zone, you can check for the latest version of this guide. Find related deployment guides, design guides, and white papers at the following pages. So I did get it from here, so yep, this is the same version, updated May 4th, 2020. And yep, I'll definitely be using this in the future, definitely for data center, digital network architecture. Yeah, lots of stuff on here, lots of good stuff. SD-WAN, that's a big one I want to. Cloud. Now this is for devices, right? I don't know. Yeah, I definitely want to do this software-defined WAN sometime. It's a huge buzzword. If you just do jobs and then type in SD-WAN, I'm sure there's a lot of hits. Let's see. So this is Google Jobs, so let's search for SD-WAN. And we'll search for it with a hyphen as well. Or I guess with a hyphen it pops up. But yeah, let's see how many hits we got. So we've got a total of it does not say at all. Okay, it just doesn't say how many total hits I got. Which is literally the only thing I wanted to know. There is nothing else I wanted to know except for how many total jobs are there with SD-WAN in the title. But that's the only thing I can't know because this site is not doing it for me. Let's try LinkedIn jobs. Ah, okay. Well, that's interesting. Now, this is limited to where I am at right now. Um, but it looks like we only got 42 hits. Let's try it with the hyphen. Okay, we got a few extra, but we still only got 52 hits. That's interesting. I thought SD-WAN was kind of a more lucrative thing. Yeah. That is interesting. I was not expecting that. Looks like a lot of these are like VoIP based, like based with like phones, telephony. I don't know if this one is. Huh. Yeah, but here we got one that's phone. Got, well, I guess not that many are phone. Another one that's phone. So far only 2 of them. But in any case, I think that will be something to look into. I don't know. Like at the same time, like I could dive deeper into like security or like, because let's see how many hits we've got for network security. Yeah, we got nearly 2,000 hits for network security. Now, granted, network security is just a less of a, it's more general of a term, so, you know, it's not a specific jargon term. So what is I wonder what's a specific jargon term in network security that would be comparable to learning SD-WAN. So I guess Scapy, because that's a Python library used in network security. So it looks like we only got one result for that. Yeah, and you can see we've got network security showing up in this one as well. Wow. It's a lot. Okay. All right. Design campus LAN and wireless LAN. Designing a LAN for the campus use cases is not a one design fits all proposition. The scale of campus LAN can be as simple as a single switch and wireless access point at a small remote site or a large distributed multi-building complex with high-density wired port and wireless requirements, like an airport or a hospital. The deployment may require very high availability for the services offered by the network with a low tolerance for risk, or there may be tolerance for fix-on failure approach with extended service outages for a limited number of users considered acceptable. Platform choices for these deployments are often driven by needs for network capacity, the device and network capabilities offered, and the need to meet any compliance requirements that are important to the organization. Traditional access, dedicated distribution, and access layers, L2 or L3, you must impose most of the campus wired LAN design complexity when aggregating groups of access switches by interconnecting the access layers to the distribution layers. If devices connecting to the access layer have a requirement to communicate with a layer 2 logical adjacency, and those connections cover multiple physical wiring closets connected to a distribution layer, then it is possible to adapt to the traditional multi-layer campus design to address the layer 2 adjacency needs. However, the traditional designs drive more complex configurations with additional protocols that must be kept consistent across multiple devices. Simplified access, virtualized stackwise access, and stackwise virtual distribution. Okay, so these are platform choices. So you can choose traditional access, you can choose simplified access, which is virtualized stackwise access and stackwise virtual distribution. To improve the design, there are preferred alternatives to make the deployment easier to manage and less prone to mistakes while enhancing overall network performance. Such alternatives include the simplified distribution layer using options such as a switch stack or a stackwise virtual system, and the simplified access layer using a switch stack with stackwise technology. Both make both deployment and troubleshooting much easier for support staff. Both make deployment and troubleshooting much easier for support staff. So traditional access is the one I've seen the most, but simplified access sounds like something interesting to look into as well. The final platform choice you can use for your design is Cisco software defined access, and these are all choices for your access layers, for how the endpoints of your network are going to look like. You can either have traditional access, where it's just layer 2 or layer 3 connectivity between a distribution and an access layer. You're going to have simplified access, where your access switches are stacked together using stackwise or some other stacking technology. Or you can have Cisco software defined access, campus fabric, and automation of the distribution and access layers. A design alternative is available for organizations that either don't have the need to extend layer 2 connectivity across an access to aggregation boundary, or have other means of implementing this functionality, such as when using fabric technology for campus designs, an integral part of Cisco SD access. The alternative to the layer 2 designs is to extend layer 3 connectivity to the access layer. The implementation of a well-designed layer 3 access network ensures consistent configuration, performance, scalability, and high availability of the network versus the traditional multi-layer campus design. Yeah, so my understanding is kind of the best way to design a campus network is to extend layer 3 all the way as far down as you possibly can, and then really the only reason you would have layer 2 extended down is if a device required it for some reason. But then even at that point, you would just make a special case for that one device by using a private VLAN for it. And for everything else, you would continue to use layer 3. Kind of like a hybrid design. The motivation for the recommended design choices is not that they are the only options available, but that the recommendations highlight preferred choices given the scope of the requirements. Even though the traditional multi-layer campus design previously mentioned is a widely deployed valid design choice, the design is not one that is typically recommended considering better alternatives that are currently available. When you integrate the wireless components of the campus design with the wired components, the design can often be treated as an overlay that is dependent upon the services provided by the underlying campus infrastructure. This is especially evident for larger networks because increasing capacity with dedicated services or dedicated devices becomes a requirement. Smaller networks, such as those at small remote sites, offer opportunities for simplification and optimization that are also reflected in the design choices shown below. The primary design options are grouped by scale, and then appropriate selections are based on the capabilities desired. The selection from the spectrum of capabilities is based on the needs of a specific employee. I'm sorry, but that sounds kind of dumb. Like, why are they grouped by scale? Like, I thought scaling was something that wouldn't require groups. You'd have one group, and then it would scale up and down within that group. Like, I guess maybe they scale in different ways or something. We'll find out as we continue to read. Next section is Design Fundamentals, Campus Wired LAN. The LAN is the networking infrastructure that provides access to network communication services and resources for end users and devices spread over a single floor or building. You create a campus network by interconnecting a group of LANs that are spread over a local geographic area. Campus network design concepts include small networks that use a single LAN switch, up to very large networks with thousands of connections. The campus wired LAN enables communications between devices in a building or group of buildings, as well as interconnection to the WAN and internet edge at the network core. Specifically, this design provides a network foundation and services that enable tiered LAN connectivity, wired network access for employees, IP multicast for efficient data distribution, wired infrastructure ready for multimedia services. Okay, hierarchical. I think it's hierarchical.
Hierarchical.
Yeah, hierarchical. It's like hard to pronounce because you gotta say like kakol, which is difficult to say. But this is a hierarchical design model. The campus wired LAN uses a hierarchical design model to break the design up into modular groups or layers. Breaking the design up into layers allows each layer to implement specific functions, which simplifies the network design and therefore the deployment and management of the network. Modularity in network design allows you to create design elements that can be replicated throughout the network. Replication provides an easy way to scale the network, as well as a consistent deployment method. In flat or meshed network architectures, changes tend to affect a large number of systems. Hierarchical design helps constrain operational changes to a subset of the network, which makes it easy to manage as well as improve resiliency. Modular structuring of the network into small, easy to understand elements also facilitates resiliency via improved fault isolation. A hierarchical LAN design includes the following 3 layers. Access layer, so that's the layer down here, client access, provides endpoints and users direct access to the network. So on my network here, we're using these open vSwitch devices for the access layer, but we'll see as we read on, is that the best choice, or can I make a better choice to use for the access layer? The reason I decided to use the open vSwitch is because we've got 16 ports on them, so lots and lots of places for people to plug in. We've got the fewest number of ports on the core. Well, I guess we got the same on the yeah, so the fewest number of ports are on the aggregation, but I think Arubas are not as high powered as the Junipers. So the Junipers I wanted to be the most high powered. Next is the distribution layer, aggregates access layers and provides connectivity to services. And the last is the core layer, provides interconnectivity between distribution layers for large LAN environments. Each layer, access, distribution, and core, provides different functionality and capability to the network. Depending on the characteristics of the deployment site, you might need 1, 2, or all 3 of the layers. For example, a site that occupies a single building might only require the access and distribution layers, while a campus of multiple buildings will most likely require all 3 layers. Regardless of how many layers are implemented at a location, the modularity of this design ensures that each layer will provide the same services, and in this architecture will use the same design methods. So this is scalability by using a modular design. So yep, we've just got these things here. Oh yeah, so so this shows how it scales up. So for the smallest, so a site that occupies a single building, you've got core distribution, which it looks like it's just stacked, or it's just one device serving those 2 roles. And then you've got your access switches. You don't need as many because you don't have as many endpoints. But then as you scale up, you've got to add more core switches and more of these. Alright, access layer. The access layer is where user-controlled devices, user-accessible devices, and other endpoint devices are connected to the network. The access layer provides both wired and wireless connectivity and contains features and services that ensure security and resiliency for the entire network. So we can see what kinds of devices here would be coming off of this access layer, these switches. We've got wireless access points, which are kind of an extended access layer because handheld private devices connect up into that. We've got personal telepresence, so like a video camera, something like that, will plug into the access layer. Or a TV maybe, like a smart TV. And then IP phones, of course, which again are another kind of extended access layer because then the user picks up the phone and stuff. Alright, so Denise. I think I meant to say Denise. Alright, so this is device connectivity. The access layer provides high bandwidth device connectivity to help make the network a transparent part of an end user's day-to-day job, the access layer must support bursts of high bandwidth traffic where users perform routine tasks such as sending large emails or opening a file from an internal web page. Because many types of end user devices connect at the access layer, personal computers, IP phones, wireless APs, and IP video surveillance cameras, the access layer can support many logical networks delivering benefits for performance, management, and security. Resiliency and security services. The access layer design must ensure that the network is available for all users who need it whenever they need it. As the connection point between the network and client devices, the access layer must help protect the network from human error and malicious attacks. This protection includes ensuring that users have access only to authorized services, preventing end user devices from taking over the role of other devices on the network, and when possible, verifying that each end user device is allowed on the network. Advanced technology capabilities. The access layer provides a set of network services that support advanced technologies such as voice and video. The access layer must provide specialized access for devices using advanced technologies to ensure that traffic from these devices is not impaired by traffic from other devices, and to ensure efficient delivery of traffic that is needed by many devices in the network. Okay, so we're talking about the access layer here. I just kind of want to put this in context with what I read up here about the access layer, traditional, simplified, or Cisco software defined. Let's just keep on reading. If it ties back into that, hopefully they'll point it out as we go. Multi-gigabit Ethernet, MGIG, and PoE at the access layer. That's an important thing to have on your access layer, because certain devices like VoIP phones, wireless access points get their power from the actual device at your access layer using a technology called power over Ethernet. So an Ethernet cable has I think it's like 6 wires. I don't remember exactly. But like 2 of those wires are just kind of dead wires. So some switches will use those wires to send power over it. But you need to have a special switch port on your device. Yeah, here we go. So here's the RJ45 color code. So yeah, we've got striped and non-striped. So yeah, we've got transmit, transmit, receive, and receive. Yeah, and then we've got these NAs. So that's for like future experimental stuff, and hey, it just happened to be the case that PoE is what is being used with those extra cables or extra wires in the cable. Yeah, so 7, 8, and 4 and 5 are used for PoE. 1 and 2 are used for transmitting. I don't know what the difference between the plus or minus is. And then 3 and 6 are used for receiving. Oh yeah, the technical term is a pinout. Yeah. Alright, as customers migrate to 802.11ax Wi-Fi 6, the access layer switch platforms to which the Catalyst 9100 series access points connect may also need to be upgraded. Data rates above 1 gigabit per second supported by 802.11ax Wi-Fi 6 APs are driving the requirement for multi-gigabit port speeds, 2.5 gigabits per second and 5 gigabits per second at the access layer. The higher MMIO rates of these APs, along with the rapid adoption of IoT devices, is also driving the requirement for higher PoE requirements, PoE Plus, Cisco UPoE 802.3BT Type 3 and Cisco UPoE Plus 802.3BT Type 4 at the access layer switch ports. Oversubscription ratios. The migration to mGig may also require increasing uplink port speeds in order to maintain the desired oversubscription ratio. Determining the oversubscription ratio of the uplink when deploying mGig technology can be more challenging than traditional switches with only 1 gigabit per second ports. You need to take into consideration the number of access ports on the switch which support mGig which supports speeds 2.5 supports speeds over than 1 gig, which is still kind of a new thing. A lot of switches max out at 1 gigabit per second. Since not all switches support mGig on all ports, a lot of switches just max out at 1 gig per second. Even consider something like 100 meg to be a high-speed port. Fast Ethernet ports go as low as 10 meg per second. You also need to take into consideration the speeds at which the mGig port is capable of operating, as well as the speed at which the port will be operating. Although an mGig switch port may be capable of operating at 10 gigabits per second, Cisco Catalyst 9100 series APs only operate at multi-gig a bit speeds up to 5 gigabits per second currently. For example, let's say you deploy a 48 port switch which supports mGig up to 10 gigabits per second on 12 access ports, 1 gigabits per second on the other 36 ports, and with 4 times 10 gigabits per second fixed uplinks. However, you only provision 2 gigabit per second uplinks. This configuration would provide up to 20 gigabit per second uplink bandwidth, assuming all uplinks are active, as in a multi-chassis Ether channel MEC configuration. Example, oversubscription ratio, single access layer switch. So here we've got stacked Catalyst 9000 distribution layer switches. Here we've got, and then we've got them with port channel. We've got Catalyst 9000s, which is access layer switch. Then we've got our access points, all that sort of stuff connected. So this must have PoE then. We've got 48 port switch, 12 N-gig ports up to 10 gigabits per second, plus 36 1-gig ports. Maximum oversubscription ratio at the access layer uplink switch. So yeah, that's really important to know. What is the max my device can choose? So let's see if I chose a multi-gigabit device here. I don't know how to use this. I'm surprised I didn't see that in there. Maybe it's just hidden. No, it's not in there. Yeah, that's not a real command. Ah, here we go. Ah, here we go, apt-ctl. So that should be, yeah, it was this one that I was looking for. Perfect. Okay, let me try this command on a different device. I might have messed it up by entering in extra things. Nope. Oh, maybe I need to do start. Yeah, I kind of wanted to use this on the access layer just because it's interesting, but it might be a little bit too out there for me to use. And I'm not sure when you would use this. Like, I don't know what this is for. Like, why would you need to use open vSwitch ever? Now, I thought I learned about this in... Now, granted this is... Okay, I thought I touched upon this in a book I was reading, but this is Wired Networking, so let's put the book aside and see if I can find just a free resource online that explains this more. Okay, so I guess this OS you wouldn't really use for hardware. You'd use it if you had like a virtual switch, or you were virtualizing a network and you needed a switch for your virtual network. You can use Open vSwitch for that. Let's watch a video on this because I'm just curious what this is. Yeah, what is it?
In this video, I'll cover an introduction to Open vSwitch, in which I'll primarily focus on a demonstration of using OVS. I'll start with a brief definition of Open vSwitch. Then we will dive right into OVS by creating a virtual switch and using it to connect a host and two tenant VMs on that host to each other in two memorable network. All along, I'll use some simple diagrams to represent network connectivity and how it changes when components are added to OVS. Finally, I'll cover a very brief look at the architecture of OVS. In future videos, I'll look a little deeper at some features of OVS, including using OpenFlow, creating tunnels like GRE and VXLAN, as well as some other configuration options. Briefly, before we jump into a demo of Open vSwitch, what is it? Open vSwitch is an open-source, OpenFlow-capable virtual switch that is typically used with hypervisors to interconnect virtual machines within a host and virtual machines between different hosts across networks. It is also used in some dedicated switching hardware. It can be a critical piece in an SDN solution. OVS supports many traditional switch features such as VLAN tagging and 802.1q trunking, standard spanning tree protocol, LACD, port mirroring, flow export, tunneling, and QoS control. So let's jump right in and try out Open vSwitch. I'm not going to cover installation instructions in this video so that we can focus on implementation examples. During this demo, my laptop with Linux Mint installed. The laptop has an Eth0 port getting its IP address and default gateway through DHCP. So right now I simply have my IP stack in Eth0. So now I'll create a virtual switch from the shell. To do this, I'll use an OVS vsctl command. This command is used when configuring OVS bridges. So it's OVS vskettle add-br for add bridge, my bridge. Here I'm adding a bridge named my bridge. You can name the bridge anything you want. OVS vsctl or vskettle show will show us our new virtual switch. You see it has a single internal port with the same name as the parent bridge, which is my bridge. This port is also mapped to an interface with the same name, my bridge. It is marked as internal to distinguish it from the other OVS ports like we'll see later. I'll turn up this port with ifconfig my bridge up. Now I'll check ifconfig. This shows me my laptop now sees an interface called my bridge. If I change it still go up, it needs to go 1 up. 92 was 4 and 5. Use that command much. This is the normal list command. Will show you the records of it. So that's from the OVS DB server. And as I said,
yeah, I don't think those OVSs are the switches I'm looking for. It's just, yeah, I don't think that's right. I should use a different switch for my access layer. Where was I? I think I was, yeah. So let's continue reading, and we'll get to the switch stack configurations. And I might stop there actually. How long have I been doing this for? Over an hour. Yep. So that's usually a good stopping point. The maximum potential bandwidth usage of the switch ports would be 12 times 10 gigabit per second equals 120 gigabit per second plus 36 times 1 gigabit per second equals 36 gigabit per second for a total of 156 gigabits per second. The maximum uplink over subscription ratio would be 156 gigabits per second, 20 gigabit per second, or 7.8 to 1, assuming all multi-gig ports were operating at 10 gigabits per second. More realistically, you may have the following actually connected to the switch: 8 Catalyst 9100 series access points operating at 5 gigabits per second connected to the switch ports. Yeah, so it's really important to have this this equation there. So the equation is you want the bandwidth of edge ports to be less than the bandwidth of uplink ports. So that's the ultimate most important equation. Bandwidth of edge ports is less than the bandwidth of uplink ports. So the bandwidth of edge ports, we'll call it BWE, equals edge port or number of edge ports times speed of edge ports. And then that's plus at speed n plus times speed of edge port so basically you need to say x plus at speed y plus etc dot dot dot. So for this hypothetical network here, we've got 8 Catalyst 9100 series access points, and these are all operating at 5 gigabits per second. So the number of so the speed of the edge port has to be 5 gigabit per second. Okay, and then we're going to multiply that, and we can do it in any order, order of operations. It doesn't matter which order you do it, but we'll put the, you know what, let's do that second. So we're going to times this by 8, because we've got 8 of them. So I guess I'll just change the order up here so that the documentation of the equation is more clear. Okay, so yeah. But now we've got to add it for our phones. So for our phones, we've got 1 gigabit per second. But now we've got 32 phones. And then we've also got unused ports for future expansion and capability. It's unclear what those are. But I mean, I'm not sure. But for now, what we need is 40 plus 32, so we need 72 yeah. The actual potential bandwidth usage of the switch ports would be 8 times 5 gigabits per second, we have here, plus 32 times 1 gigabit per second. So that would equal 72 gigabits per second. That's exactly what I had. Therefore, a more realistic view of the oversubscription ratio is 72 gigabits per second to 20 gigabits per second, or 3 to 6 to 1. So I guess I don't know what they're talking about with the oversubscription ratio. Yeah, so this is potentially oversubscribing your uplinks. So here, yeah, so they're talking about their uplinks being 2 10 gig uplinks. That's not going to be enough if you've got 72 gigabytes you need for your traffic, and they all go and access something that sets up in the access layer. You're gonna have a influx of traffic at 72 gigabits, but you'll only have 20 gigabits per second, and you'll be oversubscribing your uplinks. This configuration provides for additional capacity in that you have an additional 2 times 10 gigabits per second unused links, as additional devices require multi-gigabit port speeds as devices transition to 10 gigabit speeds. As you expand capacity in a switch stack configuration. What the hell? Okay, that confused me because I thought like it almost seems like they're saying that it's fine to have this kind of ratio. Like I would think you would not want an oversubscription ratio. You'd want it to be under a ratio of 1. But it almost seems like they're saying an oversubscription ratio is totally fine. The migration to multi-gig may also require increasing uplink port speeds in order to maintain the desired oversubscription ratio. Determining the oversubscription ratio of the uplink when deploying N-gig technology can be more challenging than traditional switches with only 1 gigabit per second ports. You need to take into consideration the number of access ports on the switch which support multi-gig. Since not all switches support multi-gig on all ports, you also need to take into consideration the speeds at which the multi-gig port is capable of operating, as well as the speed at which the port will be operating. Although an N-gig switch port may be capable of operating at 10 gigabits per second, Cisco Catalyst 9100 series APs only operate at megabit speeds of up to 5 gig per second currently. So that's a good point, and that's what I was. So this is actually a bit of a misnomer. You don't want to times it by the speed of the edge port. You want to times it by the speed of the lowest band port speed. So if you're connecting an access point to a edge switch, and the edge switch can run at 100 gigabits per second, but the access point can only run at 10 gigabits per second, you don't need to use that 100 gigabit per second figure in your calculations. It's completely irrelevant. It'll just auto-negotiate to 10, and that's the figure you use for your equations. So, okay, and then what I'd like to learn more about is the oversubscription ratio, because I would think you would want an oversubscription ratio of either 1 or less than 1, but it looks like here they're saying oversubscription ratio of 3.6 to 1, even up to about 8 to 1 is normal and expected, and that is a surprise. So I'm going to take a quick break. When I come back, we'll look into that a little bit. We'll Google about oversubscription ratios in networks, and then I think I'll end it at switch stack configurations. So I will be back shortly after a break. All right, I'm back. So I just want to do one final thing. So first thing I want to do is make sure I have this link saved. All right, got it. And then the next thing I want to do is, I gotta think about it. Oh, right. Look at the oversubscription ratios. Here we go. Oversubscription ratios and best practices. I think I'm a part of this on. Yeah. Joined. I was looking up industry best practices, defining what is an acceptable oversubscription ratio for access user and access user top of rack switches. I found a Cisco white paper titled Oversubscription and Density Best Practices, but it discusses FCOE and not regular Ethernet traffic, online resources, IP space webinars. Regularly references a 1 to 1.2 or 1 to 3 oversubscription ratio at the TOR level in the data center. I was expecting something more like 1 to 10 or even 1 to 20. What the hell? I would assume 1 to 20 or worse would be good enough for most user access switches. Have I missed any relevant devices? See, I'm confused here now. Is he messing it up and saying 10 to 1 or 20 to 1? Because I don't understand ever having because like you're not gonna have all of your end devices pushed to capacity all the time. So having a 1 to 1 ratio is obviously the best ratio, but I think like a 2 to 1 ratio is fine, because like you're not going to have all of your edge devices maxed out all the time. So I'm surprised that he's got those types of ratios. So Sweden, the rule of thumb is 1 to 10. That is, you shouldn't have any major problems of having 10, 100 meg. Oh, yeah, you know what? They've got it flipped. So, yeah. Okay, yeah, they've got it flipped based on how it's in the design zone. In the design zone, they list the uplink first and then the edge ports second. Oh no, they list the uplink second and then the edge ports first. So it's a edge to uplink ratio. Here they're doing an uplink to edge ratio. So the uplink has 1 gig, so we see uplink here. The edge has 10 gigs, so we can see it's an uplink to edge ratio. Here we can see the uplink has 20. Which is second, and then here has 156, so it's a edge to uplink ratio instead of an uplink to edge ratio. So if this were an uplink to edge ratio instead of an edge to uplink ratio, the same way these are uplink to edge ratios, it would be 1 to 7.1. Yeah, so this is above is based on the assumption that roughly 45% of the clients are small users, 45% medium users, and 10% are heavy users. So yeah, you're not going to have, you're not going to have all your connections maxed out all the time, so a 1-to-1 ratio really doesn't make a lot of sense. This is frustrating. So this guy is doing an uplink to edge ratio instead of an edge to uplink ratio just randomly. Well, we're on Reddit here. I guess 10-to-1 is better. Yeah, and you can see they're all flopping it. There's no standard on whether it's an edge to uplink or uplink to edge ratio. So in that post, they are when was this? 6 years ago, and it's deleted now. So let me. You know what? I think I might make a new post. Yeah, see, and here gets really tricky because they don't tell you. I mean, I guess you can kind of figure it out. I think mostly it's access to uplink ratio instead of uplink to access ratio. Yeah, so they're calling it a downlink instead of an uplink, but the common ratio are 20, and then distribution it gets different. Okay, so you know what? I think I'm going to save. I'm going to save on my blog a post on so let me make a new post, and we're going to say let's say syntax equals most common syntax equals access to uplink, rule of thumb, ratio 20-to-1 access Okay, so that's going to be it for this video. Oh. Yep, thanks for watching, and I'll see you in the next video where I read about stack switch configurations.